Hello, hi friends. Good morning, all of you. Hope you are all doing good. And gradually we start listening some good news, and hopefully more and more good news in the coming weeks. Definitely expected. Now, in the last two sessions, we did the concepts of electromagnetic induction, as I told you, a very simple one. Now, today's session we'll do numericals or objectives, and in this case also. Remember, both conceptual and numericals I am doing, and more objectives also, more conceptual I am doing, taking into the history of our previous examination, because this topic, a conceptual question, appeared more number of times. Now look at this first example. He says it's a ring like this, held in the horizontal plane. Held in the horizontal plane, and a magnet like this is now allowed to fall along its axial line. Now the question can be wide open with different types of options. First one, like what happens to the motion of this, what type of motion do you expect for the magnets, and what type of EMF or current we do expect for this fall like that. Now, as I have told you, this is held like this. Supposing this one is north pole facing the coil, and it starts falling. As it falls, what happens? Since the distance decreases, flux through the ring, flux linked with this ring increases. Change of magnetic flux. What is the principle? Any case of change of magnetic flux, EMF is induced, and if it is a loop, a closed path, induced current also is there to oppose that change. Therefore, now, as it falls, and since this is a loop, there is induced EMF and also induced current that opposes the motion. Therefore, this free fall, actually when it is dropped, we expect the acceleration to be A is equal to G. Now, because of the induced currents, again I am telling you, it is not because of induced EMF, it is because of induced currents. This fall is opposed, and hence when the magnet is above the ring, it will be the case A less than G, acceleration will be less than G, right? And now what happens? Supposing it is, after a while it crosses the ring, and this time it is distance increasing between the magnet and the ring. Again, earlier it was flux linked with this ring and increasing with time. Now later when it crosses, what happens? It is increasing the distance, and the flux linked with the ring decreasing. Again, change of flux will arise and causes the induced EMF and induced current. Therefore, here also the same range principle. When it is falling, here also below the ring also, it is A less than G. So throughout its path, as we have shown, it will be A less than G. So no question of uniform velocity because of a very heavy magnets that we have taken, and we have concluded only with acceleration A less than G. Now one more thing is that you see, when this magnet is above the ring, the increase in flux was there. To remember, increase in flux caused by magnet should be balanced by a decreasing flux. So to oppose the increase, there should be a decreasing one. Therefore, if this is what is the inward flux earlier we had, now it should be upward flux we should get due to induced currents. So that induced current, as you will see, that will be in anti-clockwise direction. Therefore, when the magnet is falling, when it is above the ring A less than G, yes, but what is the direction of induced current? Induced current will be anti-clockwise sense. This is anti-clockwise sense. Whereas now when it comes the other case, here what we have shown is change is the decrease in flux. So immediately here what happens, here also A less than G, but the current, induced current we are talking about will be in clockwise sense. So this is also a difference. This is also a difference. Now, the same example, because many of the examples when we look at, we take it for granted. But sometimes a small change. What is the small change? Supposing same kind of example is given. What is the difference? Here it shows it as a ring with a small cut, and these ends you will call it as P and Q are the ends. Now in this case again, the magnet allowed to fall freely along the axial line. What will be the case of the nature of the motion of the magnet? But in this case, do remember, definitely the relative motion is there, change of flux is there, and definitely causes induced EMF, but not induced current. Why? Because this is not a closed path. Though there is induced EMF, induced current is not there. Therefore, it cannot oppose the motion of the magnet. Right? No induced current is there. So no induced current. Therefore, here what happens? A is equal to G. Here also A is equal to G. No question of any change of accelerations. One small change that you can see. So in all such cases, look for induced EMF and also induced currents. Now one more example you will see, again based on same Lenz law consequence. What is the consequence of Lenz law? Whenever there is induced EMF due to increase in flux, the induced current tends to do, yes, the decrease in flux, or vice versa. So this should be our basis for all these questions. Hope you do for. Oh, no, along with that, we also need the concept of electromagnetics, which we said, see, this is a ring or a coil. When it carries current, what is the direction of magnetic field, magnetic moment, and hence we should be able to write whether it is inward flux or outward flux, flux to the right or flux to the left. So that is what is a key point here, and that is what we are going to make use in our second example. You see here, I have shown a coil Q placed well inside another coil P. Now P is connected to a source of battery, a voltage source, and key is there in the circuit. Now here again the questions are wide range, different questions are possible. How? Now what happened when key is closed? Initially key open. When key is closed, what will be the result? Second one. Now after a long time of closing the key, what will be the results or consequences in the circuit? And now here, third type is when the key is closed for a longer time and then it is opened. Again, what will be the consequences that are possible? Now here, see, initially when key is open, no current is carried by this coil P, no coil, no current, no magnetic induction is produced by P, therefore Q, remember Q is not linked with magnetic flux. Once the key is closed, what happens? The current through, supposing as I have shown this one, the current, you will write the direction in the P. The current in the coil P causes magnetic induction and hence flux link for this Q. Initially there was no flux link. Now flux starts increasing. Flux starts increasing. In which direction? You please see. Supposing if I use our right hand principle for P coil, then it will be, yes, inward flux we are getting for Q. Key when closed, Q is linked with increasing flux and it is inwards. Therefore this change of flux will cause a EMF and hence the current. This is a closed one, and that has to now give a flux which is outwards, because earlier it was no flux and then increase of flux in the inward direction. Therefore now it should be outward direction, flux caused by the induced current in Q. Look at my order. Therefore it should be anti-clockwise current that is induced in Q when key is closed suddenly, all of a sudden. Got it? Remember here the source is a steady EMF, steady current I am talking about. Steady current I am talking about. Therefore here when key is closed, Q will be induced with the anti-clockwise current. Now as long as key is closed, then P produces magnetic induction, which is a constant in magnitude and direction, and therefore no change of magnetic flux linked with Q, and therefore no question of any induced EMF. Now finally when key is opened, after some time key is open, When key is open, what happens? When key is opened, the current through P decreases maximum to 0, and hence it causes a change in the magnetic flux as well. Earlier it was key closed, increasing flux. Now this time it is decreasing flux. Again, the decreasing flux is to be opposed by this coil by the Lenz's principle. Therefore, now you remember earlier due to the current it was inward flux. Inward flux. When it decreases, it should increase. Therefore, once again, Q will have clockwise current. Induced current will be clockwise when key is open. The same. In coil Q, we will see anti-clockwise sense of induced current when key is closed. And no question of any induced EMF or induced current when in between, because these are the EMFs that are induced, the currents that are induced instantaneously when the key is open and closed. But as long as key is closed, there is no question of any induced EMF. That is how we did it. Now see the next example also. Again a consequence of Lenz law, the example based. Here I have shown a wire carries a current I, and here this current is variable current. He says di by dt greater than 0. Current is increasing at a constant rate. Remember, current increasing at constant rate. Now here we have again two coils P and Q. One placed above this wire and another one Q placed below the wire. And remember, all of them are in the same vertical plane. Now when this wire carries current which is increasing at steady rate, what will be the case of induced currents in the coils P and Q? Right? So one more time, here two things are important. You see, the principles of electromagnetics also important here. Why? Because this is a current carrying conductor. Now remember this grip rule, Ampere's right hand rule, current in the direction. What do you observe? My fingers are inwards here. Therefore at this Q we have an inward flux, and at P we have an outward flux to begin with. And then now you see, now at P this is outward flux and di by dt is positive. Therefore the flux link here is changing. You remember that E is equal to, we have told, what is that? E is equal to d phi by dt, and that phi is equal to d dot A. Therefore this d by dt will give you as, yes, dBB by dt times A. Right? Since this will be proportional to, this will be proportional to di by dt. This will be proportional to di by dt. Therefore now di by dt is a constant and it is increasing. Therefore what is that happening? Outward flux is there. Outward flux is there and it is increasing. Therefore that change will be opposed by the induced current. And naturally what is expected? We need to have a inward. Inward means again the same right hand principle if you take this one. Therefore here at P we will find the clockwise currents. Whereas at Q we have shown that it is inward flux and increasing. Inward flux increasing means opposition caused by an outward flux of induced current, right? This one. Therefore it should be anti-clockwise induced current in the coil Q. Right? This is how two things are very essential here. Number one, the direction of the current. Here I have shown from your left hand to right hand, you see. And I said di by dt is positive, it is the growth of current. Now supposing it is from your right to left, and again growth of current or decay of current, or different possibilities you will find. So that is what is to be looked at. And do remember, our right hand principle is such a big point here, very big point to find the direction of the magnetic field as well as the direction of flux, the inward flux or outward flux. Now let me show one more conceptual but a very intelligent conceptual question. What is that? Supposing I have a wire bent in this form. It's a very long wire very long wire. I call this long wire as a ABC, supposing, and here is another wire, a small wire, and I call this wire as this part I will call. Okay, let me take this part ABC. This is D and this is E. Now supposing there is a magnetic field which is directed normally into the plane. And now this entire thing is in vertical plane. All these wires are in the vertical plane and the magnetic induction is given to be inverse. Now the question is, if this is allowed to move with the constant velocity. Now this wire is allowed to move with constant velocity. What is the direction of induced current in this loop? Whatever you get in that CDE loop, what will be the direction of induced current? And second one is, along with the direction, it can also be linked with the nature of the current, that is, whether it is a steady current or variable current. When that is linked with it, it becomes a bit intelligent question. How? First, let us see what is the direction of induced current. As I have told you, this is how it is falling, right? Now what happens? Area gradually increases. When it starts falling, area increases. When area increases, flux linked with that loop also increases. So again, increase in flux case, therefore induce the current to decrease the flux. Now what flux is there? There is now inward flux. There is now inward flux and it is increasing. Therefore we should have an outward. Outward means like this. Therefore this will be the case. Now look at this arrow again. I am telling you outward flux we need due to induce the current. Therefore it will be the current which is anti-clockwise currents that are induced. Now the question is that whether that current is a steady current or variable current. For that data is very key. Here I said this wire is allowed or this wire is sliding. This wire is sliding with a constant velocity. Constant velocity. In such case what happens? When we are writing here E, due to the change of area you are getting, right? Therefore there we have seen already dA by dt. E proportional to dA by dt. Now this principle is to be used now here. Since V is constant, what does it mean? Whatever changes are happening in these dimensions, that is all dimensions like CD increases, DE increases, CE also increases, all are increasing in such a thing that this dA by dt remains constant because it is a proportionate change of the sides we are getting. Proportionate change of sides because of constant velocity and therefore dA by dt is constant and hence this induced EMF is a constant one and hence the current that is induced in the anti-clockwise direction that we have predicted now is also a steady current, right? Now what will be the change that is possible here? Supposing if it is said not sliding with uniform velocity, rather it is allowed to slide freely in the vertical plane, then what happens? Then this fall will be with the gravity acceleration A equal to G. In such case what happens? Supposing A is equal to GT, then what is the possibility? Now I leave it as a homework for you. You try to think then what will be the changes in the sides, whether there are proportionate changes are there or something else you will get. And also you do remember this velocity will be increasing with time. So naturally all these things should give you a solution. Do it and any of the doubts you can call your teacher. See this lengthy example that I have shown. Lengthy in its structure, coiled of 100 turns, each of area 100 cm square, placed in a uniform magnetic induction, magnetic field of induction 0.25 Tesla, and if it is linked with a flux of 0.2 Weber, find the angle made by B bar with the plane of the coil. Very lengthy question but a one line answer, right? What is that? Definition of flux. You remember what was our definition of flux? Phi is Yes, we have said as A, B, cos, theta, and if it is made of n terms, yes, that is also multiplied with. So phi is equal to NAB cos theta, and here the most essential point is definition of theta. Remember theta, when we read cos theta here, theta is the angle made by, yes, B bar, not with the plane of the coil, but angle made by B bar with the normal drawn to the plane of the coil. Now in the given example, you are asked an angle. Let us come to the end. What angle that you have to write there. Now just a substitution here. Remember all of them to be in SI units. Make sure that this flux is given to be 0.2. Number of turns is given to be 100. Area given to be 100 centimeter square. Therefore 100 centimeter square means 10 raised minus 4. So this is area, and magnetic induction is going to be 0.25, and of course I am again writing cos theta. Now theta is what is the required thing. Simplification you will get it anyways, right? So what is that? This is, I can write it as 4 by 5, 0.2, and this is 0.25, 4 by 5, and look at this, square, 10 raised minus 4, everything gone. Therefore this is cos theta is equal to 4 by 5. Cos theta is equal to 4 by 5. Is it okay? Is that okay? Yes, 0.25. Cos theta is equal to 4 by 5. So theta is cos inverse 4 by 5. If I say cos inverse 4 by 5 is the angle made by D bar with, yes, normal drawn to the coil. Whereas in the given question it is asked to find with plane of the coil. Therefore our answer is 90 minus theta. Therefore this is cos of 90 minus theta, will get sin theta. So answer is sin inverse of cos theta is equal to 4 by 5 means sin theta equal to 3 by 5. Therefore answer is sin theta 3 by 5. Theta equal to sin inverse of theta by 5. This is B bar with the plane of the coil. And that is what is the key point. See, it was a very lengthy question appeared to be, and the last, the twist is very, very essential. So these are what are the points which actually decides the performance in those 3 hours. Keeping our cool, reading the question thoroughly and fully is very important. So sin inverse of 3 by 5, B bar with plane of coil, or this is cos inverse 4 by 5, yes, B bar with the normal to the plane of the coil. So that is how it goes. Fundamental definitions, very, very important. You could see that because before we do any of these numericals, we are brushing all the fundamentals, and those fundamentals which we have done in detail in the group, board examination coaching also. Please go through your notebooks more and more number of times. Remember our slogan. Notebook, word by word, line by line, page by page, more and more number of times, right? So whenever topics are going on, those topics, current topics, you just go through half an hour, 1 hour. Now look at this, one more example here. Now this example, he says, these are 4 very long wires. 4 very long wires initially placed to form a square in a region having a magnetic induction B is equal to 20 millitesla, and look at this magnetic field. It says that this magnetic field is perpendicular to the plane of this so-called square which is formed by the combination of 4 wires. Now the question is, initially this is a square of side 1 meter, and resistance of the wires are given in the data as a 2.5 ohm per meter is the data. Now B is given already. Now the question is that if all these wires, each of the wire I am writing, each of the wire moving away from one another, you can see initially they are forming a square, and now all these opposite faces, they are moving in opposite direction, all with same velocity of 1 meter per second. 1 meter per second. This is the data. A wire initially forming a square in the magnetic induction, theta is given, this resistance of the wire is given, When resistance of the wire is given, look here, it is 2.5 ohm per meter it is given, right? It is, yes, resistance per unit length is given, that is important. And now the question is that after 3 seconds, the motion has started. What is the induced current in this coil? In this coil or in the loop that is formed by the wires is the question. Now here, what is that rule? Flux change is only the responsibility for the induced EMF or induced current. How here flux is getting changed? You will find that the relative motion of these wires, either one or two or all, will cause a change of area. Change of area causes change of flux and hence induced EMF. Here what happens, since they are moving away from one another, area increases. Area increases. Therefore our definition is phi is equal to A times B, A for area and B for induction. Therefore now E is equal to this derivative d phi by dt. B is a constant magnetic induction and therefore now it is simply dA by dt. This what is the expression we got. Now what is the dA by dt? How do we make use according to the given data? So this is dA by dt, I will write it as A2 minus A1 by T. The change in area and the time required or time taken for that change is what is taken as TB into A2 minus A1. Right? Simplification. Because in all the cases the geometry happens to be square only, because initially square and all of them moving away same velocity. So at any instant of time the loop will have the same shape of square. If now here I will write what is A1. A1 is equal to 1 meter square. Why? Because initial side is 1 meter. Now you see what is the velocity which is there moving? 1 meter per second. Therefore the length of each of them increases by 1 meter per second. So here this is what is happens after 3 seconds. This is 3 meters. Here after 3 meters, this is again 3 meters. Is it not? 3 meters and 3 meters. Now similarly here also the same you will have it. So what will be the final side of each of them? See, already initially it was 1 meter. Both sides increasing by 3 meter and 3 meter. Therefore it is 7 meter. 7 meter is the final side. Therefore A1 is equal to 1 meter square. That is I have squared 1 square, right? Units. Then what is A2? A2 is 7 square. This is what is 49 meter square. 49 meter square, and this is 1 meter square. Now the substitution will give you 20. This 20 is with a submultiple again. 10 rise minus 3. What is the A2 minus A1? So 48. It is going to be in meter square, and time is going to be 3 seconds. Therefore this is 16 times 16 twos. Yes, 320. 320 into 10 rise minus 3. All gives volts. So this is 0.32 volt is the EMF, and this is where everything begins. Now that it is not asked for the EMF that is induced, but it is the induced current that is asked for. So for the current we use I is equal to E by R. See, question appeared to be lengthy, but this is what you use. I am going on explaining the things, and therefore you take it as bit lengthy. Otherwise, what is the change in area, what is the time, what is the resistance? Now, what is the final side? A2 is equal to, we got it as 7 meter. 3 plus 3 plus 1, 7 meter. Now for a square, it will be, what is the total length? L is equal to 4 into 7, that is 28 meter. 28 meter. Now what is lambda? Lambda is going to be earlier 2.5 ohm per meter. Therefore now what is the resistance of the wire? Means 28 into 2.5. This is in ohms, right? No submultiples are given. Therefore now, once you got this R value, now you can write I is equal to 0.32 by this number that you got. So 28 twos, 56, 28 halves, 14. 56 plus 14 it becomes 70. But this is what is 70, and these many amperes is the induced current. See, as you can see, it is not a lengthy example. The idea is what is the change in area and what is the time interval and what is the resistance if it is asked for induced currents, like that. Now, see, I have told you that all the examples are based on one particular concept. What is that? E is equal to d phi by dt, Faraday's second law. Now, instead of, and we have shown different forms here. How? Change of magnetic flux, one expression. Change of area, one expression. Change of orientation, one expression. Like that. We did it in detail. Go through that concept in the previous session, please. Now here, the same concept asked in a graphical method. Now the graph says a coil is placed in a space where the magnetic induction is varying with time according to this graph here shown, and it is going to be at intervals. So this is 2 seconds, 2 to 4 seconds, 4 to 6 seconds. Now you are asked to find the graph that represents time versus induced EMF. Time versus induced EMF is the question. Now here you can see here, I will write this is O, this is A, this is B, and this is C. What is that we find? O to A, B is constant. B constant means flux constant. Flux constant means induced EMF is 0. That is from 0 to 2 seconds, no change of flux, no EMF induced in the coil. Now you see the next part. If it comes to A to B, so A to B, what happens? A to B, you can see the magnetic induction is decreasing with the time. Therefore, dB by dt, which is less than 0, it is magnetic induction decreasing, and therefore there will be, yes, E greater than 0. There is induced EMF, non-zero induced EMF from 2 to 4 seconds. Now that will be decided by, as how to do, Lenz law. If this is a decrease in flux, the EMF or the current is to increase the flux. Now here you see from 4 to 6 seconds, again it is shown as a straight line 1. A straight line with a positive slope, which means that yes, from B to C, what is happening? Yes, dB by dt is greater than 0. So one more time there is increase in, change of magnetic field giving us a change of flux and hence induced EMF. Again E, I will say here not equal to 0, here also I say not equal to 0. So from 2 seconds to 6 seconds we have induced EMF, but with a difference. What is the difference? From 2 to 4 seconds it is decreasing magnetic flux, and therefore the induced current has to have increase in the magnetic flux, whereas from B to C, from 4 to 6 seconds it will be the vice versa. Therefore the induced current is reversing in the direction, do remember. And that is why if we are writing the graph for this, how is that? No. Remember, there is a dB by dt which is constant. Here from B to C or from A to B, dB by dt is constant. What was our definition? E is equal to A times, yes, dB by dt. Of course, I taken cos theta 1, all that orientation. A times dB by dt. When dB by dt is constant, E is also constant. When dB by dt is variable, then E is also variable. So that logic is more important in now drawing the answer curve. Therefore, from 0 to 2 seconds, again you write now in this time x-axis EMF, y-axis EMF, x-axis time half second. So this is 2 seconds. From 0 to 2 seconds, no EMF. Let me take here. Yeah. This is time axis. From 0 to 2 seconds, no EMF. But whereas from 2 to 4 seconds, there is EMF in a specific direction. Supposing if this is what is EMF, which is steady EMF because of steady value of d by dt, this is EMF from 2 to 4 seconds. Again from 4 to 6 what happened? The EMF is reversed in the direction. Therefore same constant EMF, but it is like this. So this is where the EMF is getting reversed in the direction. A sudden inverse of, but no changes in the magnitude, because we have shown the slopes to be the same, and that is what is the answer. Now you see whether here the given curve, the slope is constant or slope is variable. Since here the slope is constant, here also slope is constant. How? In the case of this B, this constant slope is giving here, constant negative slope giving constant positive, and it is of course constant value, but it is 0 slope. Here also we are getting 0 slope from 4 to 6 seconds. And here if the slope is 0, here no question of any curve for EMF. Like supposing in this example, if it were like 4 to 6 seconds, if I say like this is what is the change. Now all different possible changes that you can try for yourself. 4 seconds to 6 seconds. Now if this is what is dB by dt. What does it mean? Here dB by dt is gradually increasing. When dB by dt gradually increases, E also increases. Then we don't get these horizontal lines. There we get again curves with slope, positive slope or negative slope that has to be shown. Supposing if it is the case, then what happens? You tell me here I represent the change 4 seconds to 6 seconds. For this non-linear change of B, we will have this case. Yes. See here, because dB by dt increasing, EMF also increases in the magnitude, and that is why we have taken this line. This line. So, a graph given for the change in B with respect to time, or for a change in area with respect to coils, circular coils or any other coil, then ask you to draw a graph for EMF. The reverse is also possible, that you can do it for yourself. Supposing an EMF time graph is given, and you ask you to find the other graphs like BT graph or AT graphs is also possible. So now the principle is to find each of the section, what is the change, whether the slope is positive or negative, slope is increasing or decreasing. That will give you as a solution. See one or two examples on motion and EMF, a very popular topic as I have told you. There have been expressions. Remember those? Look at first example. A 4 meter wire placed in normal to keyword normal to B bar is equal to 2I plus 4J Tesla, and move with the velocity is given to be 4I plus 6J plus 8K. Yeah, let me write meter per second. Find the EMF induced across the ends of the wire. Remember our definition. Motion EMF, we have not said directly E is equal to BLV sin theta. No. You remember what was the fundamental that we have taught? Now here induced EMF is equal to, this is L bar dot V bar cross B bar is the definition. So making use of this definition, dot product rule and cross product rule. But in the very beginning, you please look at those vectors that are given. Because most of the times for NEET and CET it will be an easy options, because supposing if this B bar and V bar are coplanar, if they are coplanar, what happens? This V bar cross B bar, what happens? Or if this L bar and B bar are coplanar, then what happens to dot product? That idea will definitely give you that whether 0 is possible in this case, and immediately look for options. If they are not coplanar, then we will go for the solution. In the given example, I have given them as non-coplanar because this is in xy plane. Now what is the L bar vector? L bar vector is equal to 4K. Why? Normal to xy plane means z axis K cap that I have taken. So L bar is equal to 4K cap. Therefore, this is 4K dot, and we know the rule for the cross product. What is that? Yes, I, J, K, the first row, and first vector V bar, its components are 4, 6, 8. Next vector is B bar, the components are 2, 4 and 0. And we all know how to do this cross product. So first I am writing 4K dot. So what is this rule? Yes, I, first row, first column, then A, B, minus BC rule, it was 6 minus 0 minus 32. So this is minus 32 you are getting. Again alternate plus minus. You remember this cross product rule, determinant method. This is dot, I am writing this as a vector now. This is minus, alternately plus and minus will appear. This is now J, this second one. Now when you take 4 into 0, 0, minus 2 into 8, 16. Therefore you are getting as minus 16. Next, again alternate, positive. And when you take this K, AD minus BC will 16 minus 12. Right? Sorry, 12 minus 16. So K into 12 minus 16. So this is 4K dot. All this number, whatever we will be getting, but since you see here we are getting dot product. When we are doing dot K dot I 0, K dot J 0, therefore only we get K dot K. Here the number is 4 and here what is the number again? 4. Of course you are getting minus 4, you forget about that. So 4 into 4, that is what is 16. 16 volts is the answer. Such an intelligent question is first data. Using the data we have given vector, we have written all the data in the vector forms, then using the rule of dot product and again rule of cross product and the examples. So E is equal to BLV sin theta examples. Remember, I have also mentioned it with a stress that when it is the case of using E is equal to BLV and B happens to be Earth's magnetic induction, I have told you in the case of those wheels of a rail or in the case of the wings of aeroplane, in all such cases, we have taken BV, the vertical component of Earth's induction, not complete B of Earth, or neither this horizontal component of its BH. No, in both the cases it was BV. Remember that. One more time I am showing you one more example. In this example, see, there is one important point, a new concept you can say. Now I will explain the example. I have not written it. In fact, this is a wire bent in the form which is smooth and as well as no resistance for this wire which is bent. Now we have used one ring, a ring whose radius is small r and resistance of the ring is capital R. Now it is placed between these two edges such that the ring continuously maintains the contact with these railings. You see these horizontal railings, constant contact is maintained. Remember, this frame we have given as both smooth and as well as zero resistance. Remember that one. And this capital R is resistance of the ring that we have used, and all of them are in the vertical plane, and it is placed in a space containing magnetic induction normal, that is inward field is there. Now the question is that if this ring is moved horizontally with a velocity v, not losing any contact with these rails, find the induced current. Find induced current. Now how to use? Because we have said BLV sin theta for the case of a conductor of length L, that was the meaning. Now supposing, earlier what was the definition? Suppose if this is the magnetic induction, you remember our figure, and now this is moved like this with velocity v. This was a straight conductor that we had taken of length L. Supposing instead of straight conductor, I just change it as something like this. So this is a bent wire. Bent wire, these are the ends P and Q supposing. In such case also now this is being dragged or moved with velocities, then we will now take that straight line path between P and Q. And therefore, while dealing with such examples, we don't take the actual length, but actually we take the length between the ends. That is the concept. Now for such concept being applied for our given example, how is that? Now this is a ring, a circular ring, which I will suppose that it is made of two parts. Now this is one semicircle, right? This is one semicircle, and this is the other half of the ring, we can say. Both are of, yes, the diameter becomes 2r because radius is given to be, so radius is given to be small r. Therefore, this diameter which we have taken to be the length, because it is now moved in a magnetic field. What was the definition of length for us? Yes, the irrespective of the shape, the distance between the ends we have taken, right? That is what is 2r. Now it becomes, now this one also becomes 2r. So now we can suppose that there are two conductors, each of length 2r, each moved with velocity v in the same magnetic induction b. Therefore, each of them will acquire. Therefore, now rewrite, you see, this part induced EMF, so acting as a source of EMF. This second half is also acting as another conductor, EMF induced due to the relative motion constant, right? Therefore, now if I redraw this, what will be the case? What will be the case? Yes. Shall I write like this? Yeah. This one is due to this semicircle of the ring. Here that causes an EMF E is equal to, yes, B L V. That B, L for 2R and velocity V, of course here sin theta happens to be 1. Now similarly this part is also, the second half of the ring also, yes, EMF source, it becomes B times 2R times V. Now what about the resistance? He said that the resistance of the ring was capital R. Now this capital R lengthwise with C made into 2 equals. Therefore what happens? This is R by 2 and this is R by 2. Total length, if it is R, half of the ring you are getting if it is R by 2. Therefore this is each of EMF B times 2R times V and the resistance in parallel which is R by 2. Look at this complete one. Now this is current I1 from this one source and this current is I2. Yes, both being added here at this point. Therefore this current is 2I. This current we are asked to find in this part PQ of the railing. PQ of the railing. Therefore the answer is now not I but I will write it as I1 plus I2. Okay, I1 plus I2. Now let us do our simplification now. What is E1 is equal to E2 is equal to E? Nothing but B times 2RV. So let it as 2BRV. So I1 is equal to I2 is equal to I. Why? We have seen same EMF and same resistance what we have found as internal. It's I1 equal to I2 equal to I, which is 2 times BRV, the total, sorry. Yeah. 2 times BRV, the total poles. Both are in parallel combination. And we know that in parallel combination, common potential is there, no adding of potentials. Therefore, it is E1 I1 is equal to E1 by R1, I2 is equal to E2 by R2. Both are same because of this symmetry that we have shown here. So I by resistance. Now, what is the resistance of the circuit? We have told that for the railing it is 0 resistance. Therefore, whatever resistance is there is due to this part of the ring only. This is R by 2 and this is also R by 2. Both are in parallel. R by 2 parallel. So, what is the effective resistance of the loop? It will be R by 4 and therefore the answer is no. This is only R by 2. This is what is R by 2. I am writing for each of the I1 or I2 I am writing, therefore it is R2. So I1 is equal, so this is 4 times BRV by capital R, which is I, due to each of this segment. Therefore, what is the current through this part PQ? Therefore, now I am writing the current in the PQ fragment is nothing but I1 plus I2, which is 2I. Therefore, it is 8 B or V by capital R, smaller for radius and R for resistance, we have used. Right? A question asked in the simplest way, but the same with a small change in the data appears to be a bigger one. Well, I will definitely tell you that this is a very difficult question for me because of the time only. Time only. Otherwise, the concept you remember in this example is whether it is tight conductor or any bent conductor, when we are writing E is equal to BLV sin theta, that L how to take, not the actual whatever that is shown path of the conductor, but it is only that ends, length, distance, that is how. Hope these examples will help you for your assignments. And again, one more time I am repeating, every day I am telling you, assignments are reaching you. Please, please and please, for God's sake, you solve those assignments. Good number of variety examples are there. You will find all that is in your examination. I am again telling you, examination hall is only due to, that comfort is a gift due to, see, this is what is I call self-gift. The gift I can give to myself by very sincere practice and preparation. Hope you will do. Thank you and good day.